Hi, everyone, and welcome to Building with Instruction-Tuned LLMs, a step-by-step guide. We appreciate you taking the time to join us for today's event. We're so glad to see you tuning in from all over the world. If it's late, thanks for staying up to join us today. During our event, you'll learn how to differentiate between instruction tuning and fine-tuning of LLMs. We'll see how to use the latest models, data sets, and training tools to both perform instruct tuning ourselves and to pick up instruct-tuned models off the shelf to build powerful LLM applications designed for specific tasks through data-centric fine-tuning techniques. We're going to get right into it today. If you hear anything during our event that prompts a question, then please follow the Slido link in the description box on the YouTube page and put yours in. Also, upvote any that you see in there that you'd like to see answered at the end of the presentation. My name is Loughnane, and I'm the head of product and curriculum at FourthBrain. I'm excited to welcome my friend and colleague, Chris Alexiuk, to the stage today, as we'll be working as a team to deliver this lesson. During the day, Chris is the founding machine learning engineer at Ox, getox.ai, and by night he works as a fellow instructor and curriculum developer at FourthBrain. He is also a solo YouTube creator who builds weekly with the latest and greatest generative AI and LLM tools, as you'll see him do today. One quick note on the flow of today's event: I'll be sharing slides and high-level concepts as an introduction to coding demos that Chris will run. But first, we'd like to get started by sharing a motivating example together. Instruction: identify the odd one out and explain your choice. Input: orange, green, airplane. Chris, can you walk us through the responses that we get here?
Yeah, you bet. So in the first, half here, we have our non-instruct tune. That's our base model. Its response is orange is the odd one out, and the explanation is that orange is the odd one out because it's the only one that is not a plane, which is kind of nonsensical and doesn't really help us at all. And then for our instruction tune model, we have a much better response, which is response airplane is the odd one out. And then it gives some cogent kind of explanation here. Airplane has nothing to do with the color spectrum. It uses aerodynamics and other techniques to fly. It is not on the ground, and it's made out of metal and durable materials. So it's the improvement is pretty clear between the two.
Substantial improvement on this and many other questions that we can get with instruct tuning. Super cool to see this. We're going to see lots of examples when we see you back in the demo that's coming up in just a few minutes, Chris. See you soon. So today, I want to provide a little bit of context before we jump right into the demos. We're going to talk about the big picture of LLMs and the big picture of fine-tuning versus instruction tuning. Then we're going to see some instruction tuning. We're going to see how to leverage some open source state-of-the-art models and data sets, as well as fine-tuning techniques. And then we'll also see how we can take an instruct-tuned model off the shelf and then fine-tune that model and really dial in the input-output schema to make it very good at a specific task. Okay, so the context here is that if we look at the lineage of GPTs, if we look at OpenAI's GPT, GPT-2, 3, all of the LLMs that we've seen, they're really built on this foundation of unsupervised pre-training. This is really leveraging a self-supervised approach where there are no labels to the data, and we're essentially scraping in a ton of information from the internet. And beyond that unsupervised pre-training first step, then we do some supervised fine-tuning. That's what allows us to really dial in how good we are at these benchmarks. And the benchmarks are the classic NLP benchmarks. They're the question answering, the information retrieval, the sentence completion. And what we've seen over time is that if we just use more compute and more data, we can do better and better and better at each benchmark that exists, and even include more benchmarks and get better at those as well. So this is sort of the big picture of the LLM. Now, when we go use the LLM, we want to make sure that it's good, not at everything anymore, not at every benchmark, but at one specific thing. And that's where we get into this idea of prompting or prompt engineering. This idea of zero-shot learning is simply writing a prompt and trying to get the LLM to respond to that prompt, as we saw in our motivating example. A few-shot learning technique would be giving the LLM a few examples, maybe one, maybe several, that would all be under the guise of few-shot learning. And then when we talk about fine-tuning in this context, we're talking about fine-tuning for a specific task. So this time, maybe we have many examples. Maybe it doesn't fit in the context window anymore. And what we're really doing is we're changing the input-output schema. So it's no longer a model that does everything, but instead it's a model that does one thing. And this is sort of another way of thinking about getting started building applications. Whether we're using zero-shot or whether we're using few-shot, we're really exploring that space of all possibilities within the LLM. This is cheap and this is quick. And this is a great way to just develop your MVP. Now, as you want to really explore that particular area of the LLM, the latent space within that area of the LLM, what you're doing is you're carving out a region within the LLM that you want to work within. And so there's a lot of ways you might visualize that. I offer one here that was created with Midjourney. So if you want to sort of imagine that you're in this crazy space and you're trying to find one area of it that your application resides in, that's really what you're going to do when you're dialing things in with the fine tuning on top of the LLM. Okay, so just sort of wrapping up this idea of instruction tuning versus fine tuning before we get into it, we're really asking, what task do we want our LLM to have superpowers on? That's what this fine tuning of the input output schema when we're building apps is doing. Whereas when we're talking about supervised fine tuning done on large language models in general, that's more akin to the instruction tuning that we'll see today. Whereas instruction tuning is really a way of doing better, not just on the classic benchmarks, but on being aligned with humans, being aligned with what we expect when we give instructions or direction, and importantly, being aligned when it comes to bias, truthfulness, toxicity, and other metrics and evolving benchmarks that we see coming onto the scene all the time. So we're really saying, okay, I want to develop my LLM so that it could be any superhero aligned with any task that I might want to help a human out with. That's what we're doing with this instruction tuning. And then with the fine tuning of the input output schema, when we're taking that general and making it specific, we're now saying we want to define how a user will interact with our application. And we want to make sure that it's really clear what that interaction is like and what that superpower and what that single task that we want to get really good at is. So in short, instruction tuning enhances supervised fine tuning. It's really a subset of all possible fine tuning. It's focused on alignment with humans and it's concerned with following instructions. And then fine tuning that input output schema is all about dialing things in for a specific task. We will see both today. And first off, we're going to start with instruct tuning. Now we picked a couple of pieces of technology that are particularly relevant today that we want to show you how to deal with, how to work with. DALL-E 15K is a data set that was released with DALL-E 2.0, the open source LLM, and it contains 15,000 high quality human Databricks employee generated prompt response pairs. The structure here is instruction, context, response. And each of these pieces of data falls into a different category of instruction. So you might see creative writing, closed or open question answering, summarization, and on and on. We see a quick brainstorming example of what to put in our PB&J if we don't have any J. And these can also be used commercially. We can leverage DALL-E 15K, we can leverage DALL-E 2.0 for commercial purposes. What we're going to do is we're going to leverage OpenLlama, which is a reproduction by OpenLM Research out of Berkeley that essentially recreates Meta's Llama, which stands for the Large Language Model Meta AI. As of May 22nd, just a little over a week ago, they released a new checkpoint for the OpenLlama 7 billion parameter model. They expect their full 1 trillion token training run to be done here pretty soon. This is trained on the Red Pajama dataset. The full 1 trillion tokens is associated with that dataset. And this, again, is a commercially available and can be used for commercial purposes model. So we're going to use the OpenLlama model in addition to the DALL-E 15K dataset. And interestingly, today what we're going to do is we're going to leverage a really new edition of how to do fine tuning very efficiently. And this is called QLoRa. So this is taking sort of this big idea that is sort of an emerging best practice with LLMs, that downstream tasks, meaning more specific tasks, have intrinsically lower dimensions than the higher upstream tasks. So all possible benchmark tasks, a lot of dimensions. One specific task, not very many dimensions. So when we're doing fine tuning, we can get away with a lot less compute. And we're going to leverage Bits and Bytes, a library we'll hear more about for quantization. We're going to leverage Hugging Face's parameter efficient tuning methods. And we're also going to note, because we'll come back to this in the second demo, that QLoRa, it was released on May 23rd. So just, again, a little over a week ago, is actually an improvement over the LoRa method, the low rank adaptation of large language models method for training. And so Chris is going to walk us through all of this today. He's going to talk about quantization. He's going to talk about how to think about each of these libraries. And you're going to get a real feel for what's happening at the state of the art in code. So with that, we're going to drop the link in the chat for you to follow along as Chris shows us how it's done. Chris?
Hey, thanks, Greg. So today we're going to be looking at exactly what Greg said, which is supervised instruct tuning OpenLlama using the DALL-E 15K dataset. We're going to leverage a few very powerful libraries to get this done effectively and efficiently. The whole fine-tuning process can actually be run in Colab with Colab Pro. That's kind of the amazing power of especially QLoRa. So let's just start going through this and see how we can instruct tune. As Greg said, instruct tuning is a subset of fine tuning. So we're using supervised fine tuning to let our model get better at instruction following tasks. First things first, we got to get our dependencies. As always, we will want to ensure that we're pulling right from the GitHubs for these dependencies, since some of these libraries are pretty new and they're evolving very quickly. They're resolving bugs, they're adding new features. So pulling straight from the source is just going to be easiest to make sure that we have the most up-to-date version. In order to get our model to get better at instruction following, we have to show it a lot of instructions. And we've chosen to show it instructions from the DALL-E 15K dataset. Now, this dataset is full of 15,000 instructions. They have 3 possible fields of a context, a instruction, and a response. They also have a category column, which we won't be leveraging today, but the idea is that this method of fine-tuning for instructions works better if we let the model see many different varieties of tasks. And so the category tells us which task that particular row belongs to. Our instruction is straightforward enough. It says what to do. Context is an optional field, and then our response is the output. There are 15,000 rows in this data set. However, some of them are very long, too long even to be useful. So before we really get started, we want to just pare the data set down to sequences of more reasonable length. And so we go ahead and do that just using the select method from our data sets library. We pare that down to 14,000 rows, and we see it has a much more manageable range of sequence lengths. After that, we're just going to do our train test split. We are going to use this test split for evaluation, not for testing, but we have 1.4K rows worth of evaluation and 12K worth of actual training. Now, in order to get going, we have to convert our instructions from these 3 separate columns into one unified column that follows our desired prompt template. So that's all this formatting function is doing. We're basically converting it into 2 options. One is the context option, and one is the without context option. Very straightforwardly, the reason we do this is because the library we're relying on to do the supervised fine-tuning expects it to be in this format. So that's the reason we have to convert it. We just map this function over our data set, and then we can see that we have this new column called text, which contains our full text instructions. So you see here below is an instruction that describes a task, right? A response that appropriately completes the request. We have an instruction, and then we have a response. There you go. Now that we have our model in a more reasonable state, or our data, sorry, in a more reasonable state that the trainer we're using expects, we can go on to start setting things up on the model side. We're going to be using, as Greg said, the OpenLlama 7 billion token preview. As stated, this is being worked on constantly. So, next week, there's probably going to be the 1 trillion version out. The idea that I want to focus on here is that you can run this whole example in Colab Pro. You don't need anything more than that. And that's to fine-tune a 7 billion parameter model. You can definitely get even more extra than that if you wanted to. You can go up to 33 billion parameters. But for the sake of this demonstration, we're just going to stick with the 7 billion parameter model. And then once we have our model picked, we need to set up our LoRa config. Now, as Greg expressed, we're using QLoRa. The actual LoRa part of QLoRa is the same. So we're taking our large weight matrix that occurs on the attention layers, and then we're going ahead and we're turning those into smaller matrices that can multiply together to represent the larger original weight matrix. The reason we do this is because it massively cuts down the number of parameters that we need to train. So instead of having like an absolutely huge, 1,000 by 1,000 matrix, we're cutting that down to a 16 by 1,000 and 1,000 by 16 matrix, which has a significant reduction in trainable parameters. We have a number of hyperparameters in our LoRa config. The first is rank. The LoRa paper and the QLoRa paper both talk about rank. If you want to learn a bit more, we'll talk about it in the next demo as well. But for now, we're just choosing 16 because it's kind of a default value. There's not a particular motivation here. You can play around with all kinds of ranks, including rank 1, and find that the results are pretty awesome, even at rank 1. Next, these 2 values we're just kind of leaving as default. Same with bias. This task type is entirely dependent on the kind of thing that you're training. So if you're going to train, say, for causal, which is what we're doing today, we just have to have causal LM. If you wanted to do sequence to sequence, you would want to have sequence to sequence as the task type. So just pay attention to what you're trying to do. This dictates what you set your task type to be. And then we add the Q to QLoRa, right? So this is the bits and bytes config that's just been put out by Tim Detmers, the guy who does bits and bytes, is the QLoRa paper, right? So what we're doing here essentially is we're quantizing our information down to 4 bits, which is really tiny, right? So compared to the full 32 bits, 4 bits is like nothing. You'll notice a few other parameters here. So we have this use double quant, as well as this quant type. So the paper introduces the idea of this new kind of float, which is called a normal float, which builds on some other methods. And then this double quant piece enters because when you use this quantization method, you have some kind of overhead that's introduced. When you do the blockwise quantization, there's overhead that's introduced, and this double quant helps us quantize that overhead so that even our overhead is in a smaller format. And then we have our compute D type, which is our B float or our brain float. The idea here is that the model's weights are frozen and they are stored in this NF4 format, which is that normal float 4. And then when we have to do computation on them, we convert them, or we dequantize them, into this brain float 16, so that we can do our computations, safely and stably. But the idea here is that we do 2 layers, right? First of all, we massively reduce the amount of parameters we're using with LoRa. Then we also massively reduce the size every one of those parameters takes with that quantization method here. Next up, we just set up our model. We have our model ID, which is which is the OpenLM model, and then we pass it this quantization config so that it's all in 4-bit. We scroll on down. We're going to also load up our tokenizer. We are going to add this special token of pad. You don't have to do this for this particular model we've chosen. We could use auto tokenizer, but when you're using a llama tokenizer, normally you do have to add some extra tokens. So we just wanted to showcase that process. If we look at our model, we can see everything's in 4-bit. We're very happy about that. And you can see our layers here. The QLoRa paper actually it uses the LoRa technique on all of the layers. We're going to not do that today. We're just going to use it on Q and V. That's the default for LoRa. Again, this is just to keep things manageable for Colab, to ensure fewer people have problems with the fine-tuning experience. Next up is a big piece of technology that's fantastic. This is our supervised fine-tuning trainer. This is absolutely amazing. It's from this TRL, library, which is meant for that RLHF process. However, they also have this supervised fine-tuning trainer, which works beautifully for what we're doing today. So we're leveraging that. It handles a lot of what we need it to handle behind the scenes, so we don't have to see it, which is fantastic. All we're doing is passing our original model, we're passing our formatted data set, we're passing our test set, and then we're adding our hyperparameters. We are taking advantage of that paged optimizer. This is something that helps prevent out of memory. It's a really fantastic thing. I definitely recommend reading about it in the paper, QLoRa paper, but it's just another optimization that helps improve our experience. And then our learning rate, just kind of setting standards. You'll notice we only train this for 5,000 iterations. It's not very long. The data set itself is 12K examples. So you'll see all the results we're talking about today were done with this process. So, imagine if you threw more compute at it and more iterations, more time. I mean, it can get crazy. And then here, this is a very important particular parameter. This is what points at our newly created text column in our data set. This is actually used behind the scenes in this SFT trainer to create the packed supervised data set. So this is a critical step. It's going to take that row and then process it into our supervised data set, and it's going to be a packed data set, which means that, say we have many small examples, we stitch them all together in a single trainable row, and then we pass that through the model. So it's just to help have more efficient training when we're doing this fine-tuning process. Our max seek length is just dictated by our tokenizer and our model selection, so that's it. And then we pass our QLoRa config, which is what lets all that magic happen behind the scenes. And then we call .train. I mean, this is, it's the part that does the magic, but it's probably the least interesting. You just call .train and it trains. You love to see it. You'll notice that the training loss goes down over the course of our training. That's to be expected. We're training a model. And yeah, again, this is only on 5K iterations, and we still see a nice little learning curve there. Next up, we just export our model to the hub. This is just to make sure that we have it. Model doesn't help if it does nothing outside of the notebook. So we want to be able to export it to the hub so that we can leverage it in future projects when we're building some applications with these models. We're just going to reload it, and then we're going to look at an example. So the benefit of instruct tuning, right? We have the instruction, convert the text into a dialogue between two characters, and the text is, Maria's parents were strict with her, so she started to rebel against them. When we pass this to the base model, we get just kind of rubbish output here, right? It just repeats itself. It's not doing anything useful. It's not productive. But when we use the Instruct-Tuned model, we see that it actually delivers us what we would like, which is a dialogue between two different characters. We have this character of Charles and Maria. They have a, back and forth that you can understand. It's in English and absolutely fantastic. So with that example, though, I'm going to kick it on back to Greg to go through some more of the high level stuff.
Chris, awesome stuff. Love to see that Instruct tuning. Seeing lots of great questions in the chat. Definitely drop those in Slido, and Chris will get them answered at the end. We'll see you back in a little bit to show us how to do some fine tuning of that input-output schema. Chris, thanks a lot, man. And in case you missed what Chris was kind of going through there, some key takeaways are that what we just did was some additional supervised fine tuning on top of that open llama model. We used 15,000 data points from DALL-E 15K, only 5,000 steps of training, and the total cost of this was about 75 Google Colab compute units. That is less than a month of Google Colab Pro. This is basically nothing, for all intents and purposes of the scale of the things that we're doing here. We used 4-bit quantization, and we are going to use 8-bit quantization in the next one using the classic LoRa technique. And the rule of thumb to take away from this is that, we saw the conversation with Maria, we saw orange, green airplane. In general, these instruction-tuned models are going to be better to pick up off the shelf when you're building AI applications than the non-instruct-tuned based models. Okay, so recall that this instruction tuning was really about following instructions. It was really about doing good on new benchmarks. And where we're going now is we're going into the space of, okay, now that I am going to pull an instruction-tuned model off of the shelf, I'm going to do some additional fine-tuning. This is now not going to be supervised fine-tuning that we're going to show, but rather unsupervised fine-tuning, where we're going to fine-tune the input-output schema and really define the way the user interacts with our application. So we want our application to get really good at one thing. This is the idea of fine-tuning the structure. It's really important to think about how the user is going to use our app. What goes in, what comes out. This is sort of back to classic machine learning 101 when we talk about this level of fine-tuning. And we want to make sure nobody gets poked in the eye when they're using our app. And that's really important. That's where instruction tuning can help out. But that's also where there is no substitute for thinking it through, getting the right data, even if it's a relatively small data set, and really designing the right application from the outset. So how we're going to do this is I'm going to sort of demonstrate the application. I'm going to pull an Instruct-Tuned model off the shelf, and then we're going to see how Chris can fine-tune an Instruct-Tuned model like Bloom-Z or Blooms, as we've heard from Hugging Face presenters in the past on this deep learning AI channel. And then we can use what's becoming really an industry standard method of training, this PEFT LoRa approach for fine-tuning our AI marketing assistant. So the big idea here is that let's imagine we're in a context where boss says, leadership says, the board says that writing direct email marketing copy is now considered tedious, and it's something that really should be streamlined for the department. We believe we can create a fine-tuned AI marketing assistant to really help generate marketing copy for emails and for other marketing activities that's going to be in the same voice and tone of everything that our company's been putting out. There's obvious value here. It's going to save people a lot of time. And one key note here is that in our example, we're going to use data that's synthetically generated using OpenAI's GPT-4. However, if you were going to do this in real life, you would want to leverage data from your company in your marketing voice and tone and really curate that data in a very data-centric way to ensure that your outputs were really dialed in and aligned with your brand. But for us, we're just going to take some synthetically generated data for marketing emails, for made-up products, and we're going to leverage the Bloom model, in particular the Bloom-Z model, which is the instruction-tuned version of the Bloom model, which is a huge model. It can do tons of languages. We're just going to focus on English, and we're going to just note here that the instruction tuning was done on Bloom's XP3 data set. We've got a number of links here as well associated with this, but the big idea here is that there's additional tasks, just like the categories we saw in the DALL-E 15K data set, that it's helping Bloom get better at. So we're going to take Bloom Z off the shelf, and we're going to use PEFT LoRa, similar to how we saw in the previous example. And we're going to have Chris walk us through each step one at a time. Chris, take it away from here. Demo 2.
You bet. Okay, so demo number 2, we are talking about doing a similar process. However, this time, instead of leveraging the supervised fine-tuning method, we're just going to use unsupervised fine-tuning. We're not going to have any targets or labels, so we're just going to let that data flow through our model. We're going to leverage a few different libraries again, bits and bytes, transformers, and PEFT. PEFT really does a lot of work here in letting us be able to do these kinds of tasks in Colab. Working in that limited compute space is absolutely fantastic. We are going to be, again, training, like Greg said, on that data that has the marketing information. Anyway, Greg's already talked about that, so we're gonna get into the actual training process here. Number 1, of course, got to get your requirements. Without the requirements, we can't do anything. So got to install those dependencies. We're gonna do a much more manual process. You'll notice, in the first notebook, the SFT trainer was doing a lot of the work for us behind the scenes. In this notebook, we're going to do a lot of it ourselves. So first things first, just make sure that we have GPU available. Like the last demo, in case it wasn't clear, this is Colab Pro with an A100 GPU. So both of them are going to be using that A100. You can definitely go smaller with a smaller model, but for this process, we're going to use the A100. We're going to use the Bloom 3B model. We're going to load it in 8-bit, so we're still doing some reduction in order to get our model to a reasonable size. And when it comes to our tokenizer, we can just use the straight-up auto tokenizer from Bloom Z. Now, the difference between the two models, so if you remember from the last demo, that model had the attention layers, and there was our Q proj, V proj, K proj, the Bloom model is a little bit different. The self-attention block actually has just this query key value module that we're going to target. You can see here that we have 30 times these Bloom blocks, and each of those Bloom blocks has the following, layers in it. When we target this module, instead of just targeting one of these layers, we're actually targeting every layer called this. And so when we do our LoRa process, we're not just changing one weight matrix, we're actually impacting all of these. So that's going to be 30 of them, which is what helps us get that massive reduction in parameters. When it comes to our float, for stability, we need our small weights to be in float 32. So we just do this. This is to ensure stability. That's it. We don't have to worry too much past that. Our other parameters that we set before training just makes the training process more efficient. And then, of course, we're casting our output to float. Again, it's a stability related reason. There's not much to say about it other than you should do this when you're using this technique. Now we actually want to start talking about LoRa. I wanted to just take a brief pit stop here and talking about rank when it comes to LoRa. So our rank is basically how much are we reducing that original matrix by? So what dimensions will our new decomposed matrix pairs have? And you can see that even with rank equal to 1, which means that one of the dimensions of the decomposed matrix is 1, we have fantastic results, right? So rank is really something that you can play with. Definitely make sure that you're keeping track of your metrics. You don't want to degrade model performance too much, but this rank can be taken to the extreme and maintain a lot of the original function compared to some higher rank selection when it comes to LoRa. So this is huge, absolutely fantastic. One thing to note as well, in the QLoRa paper, they did apply the QLoRa process to all of the weights, as we talked about in the LoRa paper itself, they only apply them to the attention layers. Specifically, they chose Q and V, but with Bloom, we only have access to the one module, which is our query key value layer. So let's set up the LoRa config. We're going to choose a rank of 16 here. Again, just a default, could be anything. Up to you to decide what you want. Test it, evaluate it as you're going through training. This is a hyperparameter you can tune. Alpha, dropout, bias. These are just default values. You can play with them a bit. They don't have a significant impact, but you can definitely tune them if you wish to. You'll notice we have this extra parameter here, which is our target modules. Again, we need to make sure we're targeting the correct weights that we want to apply the LoRa process to. And so we point that at that query key value module as we discussed earlier. And the task type, again, is causal LM. For people who are like, causal LM, what does this mean? We're just talking about the idea of plopping down tokens one after the other. So it's that generative task. Causal can only look back. It can't look forward. It's not a mass language model. So that's the idea of a causal language model. If you're just hearing that term today, terminology is evolving very rapidly alongside the technology. Then we have to convert our model from a normal model into a actual PEFT model. And we do that with the very complex get PEFT model function, where we pass the model in the config and it spits out the LoRafied model, if you want to call it that. This is what I really want to draw your guys' attention to, though. This is huge. The original model called a 3B means 3 billion parameters. And then we pare that down to less than 500 million, which is less than 1%, right? So this is why LoRa is so effective. We go from 3 billion to less than 500 million, which is less than 1% of the total trainable parameters. Absolutely huge. This is why we're able to do this stuff in Colab. 3 billion parameter model in Colab, you know what I mean? Like a year ago, it would have been a little mind-blowing. We're just using synthetic data. This is data we generated using GPT. So it's, we can't use this application commercially or anything, but just to demonstrate the idea. I'll just walk you through the data set really quick. We have 17 rows. That's only 17 rows, right? Each row has a product, a description, and a marketing email. We're going to use our product, something like Smart Eyes. That's what it's called. A description, glasses with real-time translation, sure. And then it has a GPT generated marketing email, which includes like emojis and hype language and stuff like that. So, and again, this is only 17 rows. We're in Colab, and we'll see what happens. Just like before, we want to get our data into this format, right? Our instruction, our product, our description, and our marketing email. This is pretty important because we want this to flow through that model. Again, we're just training it on the generative task right now. It's unsupervised. So we don't have a target here, right? We're just letting that flow through the model. And so the format we let it flow through in is important so that we can reproduce this format and then just don't give it the email, right? So we'll give it all of this information except the email. And due to the fact that it's been trained on these examples, it will produce an email in the format we hope and expect. So just another example. To make sure this is a clear point, if we wanted to go from, say, natural language to SQL, we would have our instruction, which would indicate what we're doing. Then we would have context, which is our, natural language. And then our SQL, which is the actual SQL representation of our context. This is the idea. Again, we just need to set up our prompts so that they're reproducible. We want to be able to feed everything but the response into the model and get out what we expect. So hopefully that's clear. We're just going to map that prompt template to our data set. It's pretty straightforward. Again, only 17, rows. We're just going to use the traditional trainer. Again, we're not, no supervised fine tuning here. So we can use the normal trainer. We pass in our model. We pass in our training data set, which is our 17 examples. We've beefed up the training batch size to 6 here, just because we have extra GPU memory with the A100. If you had a smaller instance, you could use a smaller batch size, though there's no guarantees it's going to work, depending on the GPU you get from Google. If you had like really large context text, you would want to avoid using a large batch size, as it would hog up more memory. So if you have like resumes or papers, you want to reduce that batch size to stay within the limits. We're only actually training this thing for 100 steps, and we're using a rather aggressive learning rate. The rest of these parameters are pretty much just stock and bear. This particular parameter is important because we are using a causal language model, which again is plopping those tokens down in order. We have to ensure that we set MLM to false for our data collator for language modeling. Since we're using a causal model, we're not using a mass language model, so we must set this parameter to false. That's about how it goes. We just turn off warnings with this line, and then it's .train, right? And I just want to show you guys, in 100 steps, we go from kind of this, 2-1 loss as we train through the 100 steps. Only 100 steps on 17 samples, so it's definitely, there's some overfitting involved, please. That's important to understand. But the idea is that we are learning the task pretty well. We see a good loss curve, so very happy about that. Again, the next thing we're going to do is push these to the hub. If you want to be able to deploy it right away with one-click deploy, you will have to merge and unload your model. But if you're just comfortable with using the adapters, you can use just the adapters, push them to the hub, which is happening when we use model.push to the hub here. We're going to reload them so we can play with them. And then we're going to look at a example, right? So we have the coolinator, and then we say this is a personal cooling device to keep you from getting overheated on a hot summer's day. We ask it to make an instruction or an email, and it gives us, go hot with the coolinator, your ultimate cooling journey. Hey there, cool-minded friend. Do you ever feel like your head just swings off on a hot day? I mean, the idea here is that we get a decent marketing email, considering we gave it 17 examples and we trained for only 100 iterations. We get the appropriate emoji, you'll notice, like we have sun-themed emojis and water when it comes to cool. The idea here is that the fine-tuned task is able to be learned quickly, and it's much better than the original, right? Going from 0 to this is a massive step, and that's what we're trying to showcase today. So with that example out of the way, we're going to pass it back to Greg.
Chris, so cool, man. That was awesome. That was a tour de force of fine tuning and instruct tuning. Thank you for that second demo. We're going to close it out here, and we'll see you back for Q&A in just a second, Chris. So in case you missed some of those details that he was going over in that fine tuning notebook, I know it was a lot. It was definitely a lot. He was doing unsupervised fine tuning. That was sort of the description of the SQL and the marketing email coming out at the end. 17 data points and only 100 steps of training, less than 5 Google Colab compute units, and 8-bit quantization in this case. So, pennies, we're getting this done for pennies. And we're using a really massive model to kick things off with. And we could even take the quantization a bit further with the QLOR if we wanted to. In general, this process of fine-tuning the IO schema is going to give us single task superpowers. We always want to start by deciding who we're building for and how they'll be interacting with our application. We want to try zero shot and few shot prompting first with just a couple of examples. And then we really want to be data centric about curating the data that we need in order to get that fine tuning done. Beyond that, what are we taking away from today? Well, instruction tuning is a subset of all possible fine tuning. It's really about following instructions, and giving instruction is the #1 rule when you're prompting. And it's about aligning with humans and aligning with some of the more subtle benchmarks that we see coming onto the stage today. Toxicity, truthfulness, bias, etc. Fine-tuning of an input-output schema, on the other hand, it really lowers the dimensionality of the LLM that we're dealing with and allows us to focus just on one task versus a big set of different benchmarks. The rule of thumb is to always pick up instruction-tuned models when you're building. And this really means that what you're going to do is you're going to fine-tune the input-output schema on top of an instruction-tuned model, which was already supervised, fine-tuned after it was unsupervised, pre-trained. And so there's a lot of layers to this stack of LLMs as we're building with them. And it always helps to go back to the fundamentals. And remember, airplane is the odd one out. That's the other thing that we learned today. So we've got some shared resources for this event, including some additional resources you didn't even see today in the main GitHub repo. We're going to share all the links today, including the slides, including everything you saw and more with you just as soon as the event is over and we send out the follow-up. So thank you. Any questions, reach out anytime. We're going to start taking questions now. I'd like to invite Chris back up to the stage, and we're going to run through the top voted questions on Slido. So number one, would it be possible to share the slides? Jorge, yes, we have the slides ready to share. And I believe that we do have them to share in the chat with you now. Number two, what ways, Chris, are there to prevent hallucinations and ensure that the answers are coming from your embedded data or documents?
Yeah, you bet. I mean, I think this is right now the most succinct answer that I can give is putting this in an application that involves some amount of retrieval process. So leveraging something like LangChain to allow you to use source documents and then providing those source documents along with the LLM's response. As far as it comes to hallucinations in the actual fine-tuned model, there's a lot of research about that. It's kind of deep in the weeds to get into at this exact moment, but I would say the quote-unquote easiest way to get it on rails is to just put it inside an application and leverage that ability to retrieve sources alongside your context to allow users to check or you to check and ensure that the quality of the generations is not fake. So.
Yeah. I like this idea of retrieving the sources alongside of whatever gets generated, just as a way to sort of fact check whatever the output of the LLM is. I think that's a great way of going about it, one that we're seeing more and more of. So we've got another question. I know you just mentioned sort of LangChain here, and we're getting some more sort of chaining and indexing questions here. How to make an LLM learn from a PDF and answer from the given PDF?
Yeah, I mean, the repo that we're linking does provide some resources on how to get started with a tool called LangChain, which I believe is going to be the lowest barrier to entry method to leverage your fine-tuned or instruct-tuned models to incorporate your own data. We always get that question, like, how do I add my own data to this, right? How do I add my own data, man? And the easiest way, honestly, is just let the LLM do what it's good at, which is processing language, and then let classic machine learning do what it's good at, which is finding similar things to the query, marry those two together with something like LangChain. And I think that's the easiest way to get that experience. And there are examples provided on how you could do that in the repo. Yeah. So, and just to sort of triple down on that, like, we did not cover LangChain today. We did not cover indexing using vector databases. We did not cover chaining. We simply covered instruct tuning and fine tuning of the input output schema. However, when you go to build complex LLM applications, you're going to want to chain a few different things together and potentially use some really optimized database structures like vector databases. But that's for another event, not for today. Although that is, how do I put ChatGPT on top of my data? The number one question that everybody's asking everywhere, from enterprise to everybody who's actually just building these for themselves. Okay, next up. How do you handle confidential data in the LLM while still benefiting from the training? Yeah, I mean, this comes down to a number of different things you can do. So you can sanitize your outputs, just check them for confidential data, ensure you're not leaking anything. Another would be to remove in pre-processing steps all PPI or confidential information. Realistically, though, if you are really concerned about leaking potentially confidential information, it does involve extra processing steps. Without removing it from the data set, it's hard to guarantee that it can never leak. And so I would suggest some kind of pre or post processing in order to achieve that goal.
Good stuff. From Andy, we've got the question, why is few-shot learning called learning, since it is not really an extension of the prompted model?
Yeah, it's in context learning. So it is the way you can think about this is with those few shot examples, we can have the model perform these tasks that it was never trained on. And so we're calling it learning because we are teaching the model how to do the task we want it to do just through those few shot examples. There's definitely some interesting discussions around, in context learning, but the basic idea is that we're teaching it to do something that it can't do. And so there is some learning. It's not learning the way we might think about training, because it's not learning it forever and this and that, but it is learning how to do a task it can't do. And so we just call it, right?
Yeah, yeah. So that example is just something that it wasn't a benchmark that it was trained against. It's just something new that we're teaching it. That's sort of the big idea of in-context learning. Is that right, Chris?
Yeah.
Yeah. Okay. Yeah. Great questions. Keep them coming. When fine-tuning with custom data, is it better to do it on a base model, a supervised model like Dolly, or add the custom instructions to Databricks?
That is a great research question. There is not a definitive answer. There are some people who believe that actually, bringing the instructions on an already fine-tuned model is potentially actually not a great idea. There are some people who say it's like the best idea. It's just a question that's going to have to be answered more concretely through a lot of research. Right now, I would say it kind of depends on what you're trying to do. If you're doing what we did in the second example, I would just straight up, that seems fine, use something like Bloomsy or a pre-Instruct-Tuned model. We're training on so few examples that nothing too crazy should happen. But if you're talking about these big volumes of instructions, I would add those custom instructions to your debrick set or whatever instruct set you want, and then let the base model rip on that and learn those tasks.
Nice. Yeah. So yes, this is being recorded, so you guys will have the recording, no problem. How should one go about getting started with LLMs? And where do you see sort of the future of LLMs headed? We heard a lot from beginners today in the chat and in the questions. A lot of people a little intimidated by some of the stuff that they saw today. How would you recommend a beginner getting started, and where should they think about where this is headed?
Yeah, I mean, I think honestly, the best way to get started right now is just to get started on something. I think the easiest place to get started is something like, querying ChatGPT through Python, the building an application on top of that, and then moving into this fine tuning and everything like that. These fine tuning processes with LoRa are great because they can be done in Colab. If you use smaller models, they can be done on the free version. So I think those are the places where you want to get started and then build your way up to these more complex use cases. But ultimately, just getting started is the thing to do. So find your favorite tutorial online, follow it, build it, watch it fail, figure out how to fix it, rinse, repeat until you're no longer getting started.
Yeah. Get on ChatGPT if you haven't yet. Do some prompting, understand zero shot, understand few shot, and then go and get tapping into the API directly, leveraging GPT 3.5, GPT 4. If you start looking at the DaVinci models, you'll actually have some understanding now of how those have been improved over time to create that GPT 3.5 turbo through instruction tuning. And so, I think just really digging in. Chris takes more of a build mentality, which is fantastic. Other people I've heard just offering this up for anybody that might be more interested in a more conceptual approach is just really go back to studying kind of the fundamentals and the fundamentals of machine learning proper, and then sort of build up with those foundational papers, many of which have been released recently. And you can sort of start from the old or start from the newer. So there's a lot of ways to go about it, but there is a ton of information there, and it's really just important to get started. I love this question that we have next here. Oh, I've actually got a new top voted question. How does the output compare to including 17 examples in the prompt to ChatGPT?
It was worse. Of course, ChatGPT is an absolutely massive, huge model that's very good at lots of things. The difference is that fine-tuned model can run on like a single consumer-grade GPU that you keep in your garage. And so I think when it comes to resource expenditure, you wind up being able to see the benefit of in with 17 examples, the output's already not tremendously worse than GPT-4, right? It's just not there yet. So you can imagine training a bit longer, using more examples, maybe using supervised fine-tuning instead, that you can push it to be very comparable and still run on a consumer-grade GPU in your garage. That's like so I would say the output compares poorly, but the performance compares astronomically.
Yeah. And, I guess in studying benchmarks, one of the huge things to consider is efficiency of the model and performing the task at hand. So how much does inference cost? How much does training cost? And so, if privacy is an issue, this is a great dovetail into the next question, Chris, which I absolutely love. Is it possible for normal humans to build LLMs without many computational resources?
You bet. Thank you, Tim Detmers. The guy single-handedly carrying the ability to do that. Yeah, for sure. I mean, processes like LoRa and QLoRa bring these, like I said, not everyone might have GPT Pro, but we use a 7 billion parameter model, and it could be better optimized, right? We can spend more time optimizing it. Absolutely, to get it run on the free version of Colab. I mean, the idea is that if you have just the free version with something like QLoRa, you can absolutely, train these 3 billion, 7 billion parameter models. You could buy a RTX 4090 for whatever it is, like 2K or something, and you can train these models yourself in your house, right? So it's the barrier to entry for LLMs, fine-tuning, inference has never been lower, and the performance shows that it's, the models run well despite being tiny to compute with. So yes, it is possible.
Yeah, great segue, Chris. Last question. This one's been climbing the ranks here, and I think you segued into it nicely. When should we use 4-bit QLoRa and when should we use 8-bit LoRa? Pros and cons.
Yeah, I mean, the pros and cons are at this point probably not super well understood. QLoRa is a very new process. I would say that, as always, the most important thing to do is monitor metrics. So when you're training on your downstream tasks, make sure you're evaluating with whatever methods you use to evaluate, ensure that you're getting response from your users. But right now, I would say that there doesn't seem to be a huge performance difference between the two. And there's a pretty significant compute reduction. So I would lean towards leveraging QLoRa at this moment in time. But again, the research isn't there, so I'm just saying this based on my experience. Please wait for the research.
You heard it here first. Chris is going to be using QLoRa. It's it's up to you which one to pick up. We're certainly seeing LoRa emerge as a best practice. It's been around longer, but we'll see if QLoRa takes the spot. Chris, awesome. Thank you for answering all these questions. Thank you for those sweet demos. And thank you everyone out there for your participation today. This brings us to the end of today's event, brought to you by deeplearning.ai and FourthBrain. In addition to our GitHub repo that we shared with you today, that includes LangChain and chatbot examples for even more generative AI app building, FourthBrain has also put together some resources for all things prompt engineering and fine-tuning that we discussed in our recent community event. Perhaps we'll see you at our next community event on indexing and chaining, taking place this afternoon at 3 p.m. Pacific. DeepLearning.ai is also going to send a follow-up email with a survey for all attendees. We would love to hear about how to make these events even better. A select 100 will receive a promo code for 50% off a 1-month subscription to any DeepLearning.ai course on Coursera. Once again, huge thank you to Chris and to all of you joining us today. We'll see you next time. And until then, keep learning. Bye, everybody. See you next time.